I want to talk to you a little bit about embedded systems at large. And specifically, I want to help you understand how the embedded system that I'm holding in my hand, the one that you're going to be working with, actually has the right building blocks, and compare it with a production grade system. The reason I want to make this comparison is because I want you to feel confident that you're actually learning with a real embedded platform. And the lessons that you pick up in this particular course are actually something that are transferable well outside the course itself. And that's important because I want you to be a TinyML engineer when you finish this course. So let's start off by talking about what an embedded system is. I talked about this in part 1, and now we'll go in deep. Specifically, any given embedded system has got 3 fundamental building blocks. The first is the input stage, where you get the input from the sensors. This is usually analog. The second is the digital phase, where you actually process all of that analog signals and try to make some decisions about it. And then the third stage is actually the output stage. Typically in an embedded system, the output may be an analog output or a digital output. Let's take a real world example that you actually understand what these are. For example, if you look at a Fitbit might be looking at the angle of rotation of the wrist based on the IMU data that's coming in, might be looking at the temperature or your pulse. And the data is then sent over to your processing system, which then actually runs the routines that were engineered by the Fitbit engineers in order to make some sort of decision and then to act on it. And that actuation might be in the form of actually generating an output to the screen, or might be recording the data into an actual subsystem. Now let's take something that we find in our houses, a thermostat. A Nest thermostat, for example, has a temperature sensor that detects what the temperature is around it, or might have a rotational sensor which detects how much you're actually changing the dial so that it can, in reaction, actually update the screen so that it tells you what the new setting it's reaching out for. Now, these are production grade systems, and I want to make a connection between these production grade systems and the TinyML system that you have in your hand. So let's take the Echo Dot, since we are often talking about keyword spotting. An Amazon Echo Dot reacts to Alexa. How does that happen? If we take it apart, we see different components in there. And in this teardown, we are seeing that the microphone array is on the PCB. And there are 4 different microphones here that are actually the source of the input signals into the computing subsystem. These Texas Instrument microphones take the data and hand it off to the processing system. From a processing standpoint, you actually see 2 different computing engines here on 2 different boards that are inside the Echo Dot. This actually should remind you of the cascade architecture that we spoke about, which is something we spoke about in course 2. Cascade architectures are extremely critical for deploying keyword spotting efficiently. So we have a small processor that does the local processing and then hands it off to the larger processor to then do further processing. And the third stage is the output stage, which, once you're finished processing the data, you actually want to actuate the input process data. And how does this compare to your embedded system? On the left-hand side is the Amazon Echo Dot PCB, and on the right-hand side is your embedded system. One of the key differences is that on the left-hand side, Amazon Echo Dot is specialized for one particular task. It does one thing, and it just listens to analog input signals, processes it, and then generates some sort of output on its speakers. Your microcontroller actually has a bunch of different capabilities. It's much more general purpose. That said, there are very strong similarities between 2 of them, specifically from the microcontroller standpoint. All the limitations of memory compute and so forth that we've talked about are actually very much identical. So that should give you confidence that when you're working with this microcontroller, you're very much working with a production grade system. So let's get a little bit deeper into the developer embedded system and contrast it with the real embedded system. The punchline is really this. The real embedded system is designed to perform one particular task. The developer embedded system has a lot more bells and whistles because it is a developer platform and allows you to explore different things and is extensible. So you have a processor and Bluetooth. You have a microphone on your embedded system. You have an IMU, a temperature sensor, a humidity sensor. You also got physical I/O ports so that you can actually interface the embedded system with your computer. And you don't have this sort of flexibility and features, this general purpose flexibility on your Echo Dot. Why? because this is a developer system. You've got a couple of extra bells and whistles, all of which actually lead to an increased price on the board. Now think about it. An Echo Dot doesn't really need to be general purpose. It's got one functionality. So you tend to strip down all of these things and make it very focused so you can keep the cost as low as possible, because it just needs to perform that single task and perform it well. Now, while we're talking about this one particular microcontroller board here, there are many different embedded systems. Later on, I'll explain why we have chosen the Arduino microcontroller board. For example, here is a HiMax AI development board. Much like the Arduino board, it's a development board. It's got a camera module on it, and it's got a microcontroller right next to the camera module. It's got an I/O subsystem that allows you to interface with the computer. Here's another example. It's a SparkFun Edge 2 that's got an Ambic microcontroller, which can also interface with your computer. It also has the exact same constraints as the embedded system you're using. The ESP-I, it's got a camera on it, it's got a small microcontroller, and the form factors are all about the same size as the Arduino microcontroller. Why am I talking about all these different devices? The reason is because there are different kinds of embedded platforms, and when you're actually going to work on these platforms, you need to know a little bit about them so that you're actually knowledgeable about something, when it does not work or how you can fix them. All of these systems come with a wide range of capabilities. Specifically at the board level, what you find is there are differences in the kind of sensors that they support. For example, the HiMax has an accelerometer, microphone, and a camera, whereas the Arduino, on the second row has got a wide range of sensors, as I already hinted at earlier. So there are some differences that we end up having. In addition, there might be differences in the kind of communication module some might provide. For example, the HiMax does not provide a radio option, whereas the Arduino and other devices have the Bluetooth capability, some have Wi-Fi capability, and some that you will actually use, with your magic wand. In addition, the embedded system has, microcontroller, which has got the processing engine, the memory, and they're tightly coupled together. Now, there are differences in there as well. As you can see, the clock speeds go, from all the way up from 400 megahertz to as low as 48 megahertz on the SparkFun Edge 2. That said, they are roughly in the same ballpark, and they're all in the order of megahertz, not gigahertz. As for the memory, they're also very limited. They have a very little bit of flash, very little bit of RAM. So these embedded systems are roughly the same in terms of the constraints. So they have different levels of flexibility. We happen to choose Arduino microcontroller because it gives you a lot of different sensors, which allows you to expand well outside the scope of this course, while also having the right set of constraints. It gives you that particular practical hands-on feel about dealing with the microcontroller. With that said, in the next video, I'm going to talk about and go a little bit more deeper in the understanding the characteristics of the microcontroller itself. And after that, we'll talk about the software and the I/O, and so that I can bring all of this together. And at the end of the day, you can feel confident by the fact that you're working with a production grade microcontroller that's actually found in real world devices.